So let us get started with the very basics. What are the absolutely bare bone essentials that you need to know about the electron? You need to know that an electron has a one negative charge. It has a negligible mass. That does not mean that it has no mass. Electrons, after all, is matter, and matter has mass. But we use the word negligible because, for all intents and purposes, you can neglect its mass. It spins around the nucleus, so the protons and neutrons are inside the nucleus, and the electron spins around the nucleus. And probably the most important one is that it is responsible for the chemical properties of the atom. Now, as the title of this next slide will make it obvious, I'm going to explain the two types of electrons that each atom has. In front of you, you will see this spinning atom of sodium, symbol Na, and has 11 protons and 11 electrons. Now, let's pause this animation for a second. What you notice over here is there is one electron in the outermost ring, followed by 2 plus 8, 10 electrons in the inner circles. This is a very common diagram of an atom that you must have learned in your middle school science classes, and it is inherently not incorrect. However, it is not the most accurate representation of an atom, as you will learn later on in this video. So let us go ahead and define the two different types of electrons. We're going to say that this is your valence electron, and all of these, okay, I'm not going to draw 10 different lines, but you get the idea. We are going to call them the core electrons. So then the next question that should come up in your head is, well, if they're all electrons, why differentiate as valence and core? And the biggest and the most important reason behind differentiating is that think of the valence electrons as the currency of the atom. These valence electrons are the ones that are going to potentially leave the atom and go connect to some other atom. Okay, the core electrons, on the other hand, they belong to this sodium atom in a much stronger capacity. Sodium is not going to like giving up any of its core electron. As a matter of fact, any element, for that matter, will never willingly give up its core electrons without giving a major fight. And so if that is the case, then how do we figure out how many valence electrons and how many core electrons does each element have? So luckily for us, we have a periodic table. The periodic table, I kid you not, is probably the best cheat sheet in chemistry that has ever existed. Okay, all you need to do is just know where to look. So for example, on the periodic table, we know that the columns are called groups and the rows are called periods. The simplest way to remember this is you look at your A group elements, which are right here, and then your B group elements. For A group elements, okay, group number is equal to valence electrons. What does that mean? It means that if I'm looking at group 6A, element oxygen, because it is in group 6A, it has 6 valence electrons. Magnesium is in group 2A, so it has 2 valence electrons. But wait, there's more. All group B elements, which is these right here and these right here, they all have 2 valence electrons. So all B group elements have 2 valence electrons. That's all there is. So for example, if magnesium is in group 2A and has 12 total electrons, 2 out of those 12 are valence, which means 10 core electrons. Sodium has 11 total electrons, 1 valence electron, again 10 core electrons. And I want you to notice a pattern. Elements that are in the same period have the same core number of electrons. So sodium has 10 core electrons, so does magnesium, so does aluminum, so does silicon, so does phosphorus, sulfur, chlorine, and argon. They all have 10 core electrons. What's changing is the number of valence electrons. This right here is called the S block. This right here is called the P block. These elements in the middle, they're referred to as the D block. And the elements on the bottom over here are referred to as the F block elements. If you remember, I told you that S block can hold 2 electrons. Look how many columns are in S block on the periodic table, 2. The P block can hold 6 electrons. There are 1, 2, 3, 4, 5, 6 columns in the periodic table in the P block. And D has 10 columns, F has 14 columns. Now, I don't know about you, but things like these, make me happy. So I think, moving right along, the next item on our list is a topic we have already learned, which is ionization energy. We defined ionization energy as the energy needed to remove 1 electron from an atom. So we turn to our trusty old sodium atom here that has 11 electrons. You should now be able to tell me that there is 1 valence electron and 10 core electrons. Now, if you want to take an electron away from any atom, for that matter, okay, metal, non-metal, doesn't really matter, the atom is not going to just give it. It is you're going to have to spend a considerable amount of energy in order to coax that electron out of the atom. Some elements give up their electrons easily. Some elements really give a fight. Okay, so now we need to think of ionization energy as the energy you are going to have to spend in order to extract an electron. The first electron that the atom will give up with relative ease is the valence electron, so we call it the first ionization energy. We call it the first ionization energy because that's the amount of energy you will need to remove the first electron from the atom. Obviously, the electron that's on the outermost shell is going to come out the first. The electron that is the innermost shell will come out last, which makes sense. What if you want to take out even more electrons? So once you have taken the first electron out, now you have 8 other electrons to choose from. So let's say this is your second ionization energy. This would be your third. This would be your fourth, and so on and so forth. And the trend here is each successive ionization energy is going to be bigger than the previous one, meaning the first ionization energy is lowest, the second one is higher than that, the third one was higher than the second one, the fourth is higher than the third one. It might get a little confusing, so let's look at an actual bar graph. So here's a picture from my favorite chemistry book. It might look a little intimidating to begin with, but just basically forget about all these units and all these, fancy numbers. What we're comparing in this particular table is period number 2, which starts from lithium, ends with neon, and sodium again. What I want you to notice is, first and foremost, the number of valence electrons is steadily going up, right? So lithium has 1 electron, beryllium has 2, boron has 3, so on and so forth, until you reach neon, which has 8 valence electrons, and then goes back to sodium having 1 valence electron again. Now let us compare their ionization energies. You will notice over here you see IE1, which means that is the first ionization energy. IE2 is the second ionization energy, and so on and so forth. Lithium is a very small atom. It has 3 electrons, out of which the first outermost electron is the valence electron. The first ionization energy for lithium is 0.52. The second ionization energy jumps up to 7.30. It is fairly obvious to note the difference between how big the gap is between the first and the second. Then we look at beryllium, which has 2 valence electrons. You're going to need 0.9 to remove the first valence electrons, and then 1.76 to remove the second valence electron. If you compare to the first, the second ionization energy is not that big. Then you get to 14.85. Notice how this area is shaded in blue, and it says core electrons. And if you remember, I told you that in order to remove a core electron from an atom, you have to spend an enormous amount of energy, which I think should be fairly clear from this table. As you go down, you see the same trend. Then you get back to sodium, and suddenly you're beginning at the new period. You have 1 valence electron, so the first ionization energy is small, and then it jumps up again. Okay, so we don't need to go into much more detail, but what I do need you to understand up at this point is that there are 2 types of electrons, valence electrons and core electrons, and it is relatively easy to extract valence electrons from an atom. It is very difficult to remove a core electron from an atom. Now that we've thoroughly talked about how to and where to remove the electrons from, it is time to learn how to organize electrons in an atom. For example, when we say that sodium has 11 electrons, you cannot just throw 11 electrons in an atom and call it a day. Each electron needs to have a very specific place, kind of like how people have a specific place in a city where they live. So I want you to think of an atom like a city. Just like a person's address is always city, street name, and house number, but in the reverse order, the electron lives in an energy level, which is what you've always thought of as the rings that you see around the nucleus. From now on, we're going to call them energy levels. They're always represented by whole numbers. So you'll have energy level 1, 2, 3, so on and so forth. Then each energy level, depending on how big it is divided into sublevels. Those sublevels are denoted by lowercase s, p, d, and f. It is important that we remember their sequence. Smart people don't forget. And then each sublevel is further subdivided into orbitals, kind of how a street has multiple houses on it. If it's a long street, right? If it's a long street, it's going to have a lot of houses. If it's a small street, it's not going to have as many houses. Just like that, S sublevel is very small, so it only has one orbital. Okay, so we'll note that down. S sublevel has one orbital. P sublevel is slightly bigger, so it has three orbitals. D sublevel has 5, and F sublevel has 7 orbitals. Now, one cool thing about an orbital is that no matter which sublevel it's on, it can only hold 2 electrons. So 1 orbital times 2 electrons, 3 orbitals times 2 electrons, 5 orbitals times 2 electrons, and 7 orbitals times 2 electrons, which gives you a total of 2, 6, 10, and 14. These numbers are the maximum number of electrons that each sublevel can hold. So S sublevel can hold 2 electrons, P sublevel can hold 6 electrons, D can hold 10, F can hold 14. Now here's the cool thing. If we go back to our periodic table, at this point you have learned a really solid understanding and foundation of what are the basics of electron configuration. You have learned that electrons live in very specific places. We call them orbitals. A sublevel has multiple orbitals, and each energy level can have multiple sublevels. And so with this, we will conclude this video, and I'll see you in the next one.